Welcome, everybody. Today we're going to be working on our Unit 3 um, material here, which is to kind of revisit using Python and mathematics. This is part 2, following up from last week's lecture materials. The topics for today basically are these. We're going to look at two really important aspects of working with math relative to doing machine learning, and that is understanding linear algebra and its importance, and then this concept of dimension reduction for data and why it's important and what does that even mean, right? And I think for a lot of us, this stuff was always defined in terms of formulas, if you ever heard any of it before. And as we do the linear algebra stuff in particular, a lot of it should kind of smack of some stuff that you've ideally have learned before. And maybe when you were taught, it was all formulas and work this equation and what's the answer to number 3 or something like that. And it's a turnoff. I mean, let's face it, the way math is often taught turns people off, and therefore they don't really ever incorporate what it really means, and shy away from it. And unfortunately, when we get into the world of IT, math is a necessary aspect of it. But my hope is that maybe a different approach to learning some of it will ease your mind and eliminate the stress of the concepts that come with it. We'll start with linear algebra and why it's important for AI. And here's the answer to that question. It says here, understanding of linear algebra will be able to develop better intuition for machine learning and deep learning algorithms, and would not treat them as black boxes. And this is often what happens. We throw things into equations, the numbers come out, we assume they're right. We don't really know how it operates or what it does. But hopefully this will demystify a little bit of that for you. It says this would allow us to choose proper parameters and develop better AI models. So if we understand the math, at least in principle, and we can leverage it to our advantage, that's what we want. We don't have to come up with the ideas. We just have to use the formulas and then have them fit what we're doing computationally. Now, there's a series of like little motion videos here, and I'm just going to get them all playing at the same time so you can see them. But just to give you an example, like where linear algebra is used today, right? And so, for example, in machine learning, we analyze loss function and regularization and covariance matrices and support vector machine classification. In NLP, we use it to do word embedding and latent semantic analysis. Yeah, that's done with math. You think it's done with words, but yeah, some of that is math-based too. And then in computer vision, we have image representation of what we call tensors, and then convolution and image processing. And if you notice, these are the 3 primary areas of AI, right? Machine learning, natural language processing, and computer vision. And granted, there's more use for it in machine learning than some of the other areas, but the other areas rely on these linear equations also. It's not just machine learning, right? So math is used even in spots where you think it's not, right? I think the language one is pretty telling. All right, so it says, let's understand its importance with an example. So let's take a look at this next slide here. And what this next slide is saying to us that we basically have 2 types of points that are ending up on this graph, the orange ones and the blue ones. And generally, the orange ones are ending up on the top right, and the blue ones are ending up on the bottom left. And we can see pretty easily that there's some that overlap. There's a couple of straggler blue ones here and a couple of straggler orange ones here. But generally speaking, there's this divide. And notice that that's a linear divide, right? There's some exceptions, but generally all the orange ones are there, all the blue ones are here. And so they're looking here at that there's 2 types of points plotted on a graph, points of similar color. Can you tell where this person came from? England, probably, right? When they misspell color, or were misspelling it by their perspective. And then we kind of make an arbitrary choice, right, to like where to put that dividing line. We can do it visually. And one of the advantages of working with visuals is you can see things, right? And you can see how the data lays. And that's what's going on in this situation, right? This is a two-dimensional graph. There's two data points to plot any one of these points. It's got to have an X value and a Y value. And soon we'll learn that, X's and Y's are very subjective, right? All right, so it says first, we must determine the property of the dotted line first, and that can be done with the help of linear algebra. All right, very nice, nicely worded there. Therefore, let's understand the properties of different shapes and figures and spaces. Right, so this is kind of to give you a little bit of a fundamental understanding. And when we start plotting things, we start to call it charting or whatever. But in reality, in mathematics, these are really vectors, and we're plotting the vectors inside of spaces. What kind of space? Well, the space depends on the number of vectors and the types of vectors and how many data points are carried with each one of those. So it says when we're working with a point vector on a two-dimensional graph, so an X and a Y, kind of like a flat piece of paper, looks like a piece of graph paper, right? We can plot a point, and it says point P at unit 4 in the X coordinate and unit 3 in the Y coordinate. So we go to 4 on the X goes across usually. And so we go to 4, and the Y point is 3, and where they meet is point P, and that point P has the coordinates of 4, 3, X, and Y, right? And so this is technically, that point is technically a vector. And I also want you to notice that instead of using X and Y, what we do in a lot of like theoretical linear algebra is we'll just call it, well, X is a variable, Y is a variable. We're going to have lots of variables. We'll probably run out of letters eventually. So let's just call all of them X. And instead of giving it X and a Y, we'll use sub numbers. You notice how these numbers are a little smaller than letters. So X1 is the X, X2 is the Y, but we'll call it X1, X2, and they're each worth a certain value. And if we had more variables than that, we'd call it X3, X4, X6, X20, X1 million, whatever. All right. So that's a two-dimensional thing. When we start to look at a three-dimensional vector, we have 3 points that we're contending with. And usually when we're working with X and Y, we'll have, for example, notice there's an X-axis and a Y-axis, and this is kind of rotated in a weird way, but this is the X. So normally this is the 0 point for the X. This is the 0 point for the Y. And when you have 2 dimensions, you form a plane, right? You have an X and a Y, you have a length and a width, but it's flat. There's no other dimensionality to it. When we add a third point, that could go on the Z. So, and this is very common, like when we do computer graphics, for example, like 3D animations, you think of the X, the Y, and the Z, right? And we are not only plotting stuff, in an X and a Y, but we're adding a Z dimension. So it's coming up off the graph by 1. So the X is 2, the Y is 3, right? X is 2, Y is 3, and the Z is 1. And where do those meet? Right here. But it's 3-dimensional space. Now, in 2-dimensional space, like my screen, I can kind of represent 3-dimensional space, but it's not really what it is, right? This is flat on the screen, and we're kind of visualizing that it's dimensional, right? And this is 3 dimensions. So this one has an X1, an X2, and an X3. And it's a 3-dimensional vector in a 3-dimensional space. All right. What happens, though, if we start adding dimensions? All right. If I have 4 dimensions, well, I had a hard time drawing 3 dimensions in a 2-dimensional space. How am I going to draw 4 dimensions in 2-dimensional space? This really gets kind of challenging. And that's what this next slide is about. Because conceptually, we can't visualize it in our heads. It's not feasible. Here's the why. Because we exist as human beings in a three-dimensional reality, right? And right now we're conversing through Zoom, which gives us a two-dimensional plane to kind of share our stuff with. But we conceive in three dimensions. So for us to visualize physically a fourth dimension is not possible in three-dimensional space. People do try. And I'll give you an example. There's this thing called a tesseract, right? Um, and yeah, I'm going to do a tesseract GIF here, and I'm going to see if I can load it up, and if it'll there it goes, right? So when we have a cube, right, that's a three-dimensional thing. But when we add a fourth dimension and you rotate it, this is what it would look like if you rotated a four-dimensional object. And it's called the thing is called a tesseract, by the way. Very, very hard to understand what we're looking at, but it's basically a four-dimensional cube that's rotating. Doesn't rotate in any way our brain can comprehend, but it's really weird to look at, right? So how do we do math with that? Oh my God, right? So this is kind of the point of this. We can't visualize that, nor can I draw a graph of it. However, we are working with data sets that are really huge. Now, one really interesting movie that came out a few years ago, and I don't know how many of you saw this, the movie Interstellar, and the guy like flew off, to a planet, and then he got like delayed in time or whatever, but he went into like the black hole or whatever, and he was like in like traversing four-dimensional space. So he was traversing time as well as space, and so he was able to find a way to communicate with his daughter back home that way. It was really bizarre. If you guys haven't seen the movie, it's a really pretty decent movie. And scientifically, it's pretty accurate in terms of like the space travel aspects, the gravity of a black hole, four-dimensional space, time delays, and all that weird stuff. They were pretty accurate scientifically on all that stuff based on today's theories, but very, very difficult to visualize. But in the movie, it was this scene here that you see a screenshot of, where he was basically visiting back home and interacting with back home, but doing it at various points in time, and what was like a minute to him was like a lifetime for his daughter back home, if you remember the movie. Anyhow, this was the way they represented it, and it was really interesting how they did it. I thought, because it's very hard to really kind of even conceptualize that, and to try to put it into a movie even harder, right? All right, so if we're working with data sets that have more than three dimensions, we have problems when it comes to graphing, right? Here's an example of a three-dimensional plot shown in a two-dimensional space, right? And it's kind of rotated so we can kind of visualize it. All right. When we're working with vectors, though, vectors can happen in two different ways. We can either have columns of vectors, so the numbers are like in a column in a table. We're not going across. It's kind of like a Python list, but it goes vertical instead of horizontal. But there's also the row approach. So we can do row vectors or column vectors. And sometimes we need those data shapes in order to work with our representations. All right. Let's take a look at some sample data here. And as I'm just going to put this out there, as data analytics students, you guys will probably hear about this data set a lot, because it's one of the earliest data sets that was developed to talk about data, at least in the modern era. And so back in 1936, this guy named Fisher created this paper where he did all these measurements of irises, right? And he created this data set. And what he did is he listed all the different types of irises, and then he took their sepals, I guess they're called, their lengths and widths, and the petals and the lengths and widths, and put it all in a table with measurements, along with what particular subspecies of an iris it is, right? And notice like the data sets here, we have length width of the sepal, length width of the petal, and then we have the species. These are all numeric. This is just a descriptor. So from a numeric standpoint, we really have four sets of data, or it's four-dimensional data, right? And this is the weird data stretch here. So something can have four data points, but I can't make a visualization of it, right? At least not in the conventional sense. Because the information is already in a table, we can take the numeric aspects of the data and put them into a row vector. And the name of the species can be the descriptor for it. So we could write like Python code that looks just like that. That looks like a Python list, right? There you go, right? So it is four-dimensional. And each one of these rows would have its own row vector, right, with all those data points. So like, and really what they're trying to tell you is every unique flower has all these data points that are unique unto itself, but I can't really plot that, not in a conventional sense. Now, we discussed some of this last week about like doing math on top of vectors, and it's kind of like way out there kind of stuff, but it is possible. And what they're showing us here is this general form that if I have one vector that's one row, a different vector that's a different row, and I want to combine those two vectors or the data from those two vectors, I could set them up in data rows like this, right? Each one by name with the data points. And then I could do a command to add them. And in principle, what happens is each corresponding value, so 5.1 gets added to 4.9, etc. And then you go through and do the math, and then the combination, and I'm sorry about that, the combination vector comes up to be a new row vector. So adding two row vectors together gives you another row vector with a different set of data. When we're working with the product or multiplying vectors, is another common operation. We talked about this last time as well. And notice here they're representing multiplication literally with a dot. And that does happen in mathematics. That's one of the notations they use. And we can do the same thing. Take two rows of data, multiply each set of data, and add it to the next, right? And they all add together. And this is what we call technically a sum product. So we're multiplying and adding together, multiplying aspects, adding together, and we come up with one singular value. Now, this is kind of interesting, right? Because really, if you start thinking about what these operations are doing, is they're taking complicated data of multiple objects and combining it into one mathematical formula with a value. And then you can take it even farther when you do the dot product. And I'm taking these and I'm summarizing two items in my data set with one value. That's really pretty bizarrely powerful, by the way, right? Because now I'm summarizing two vectors with one value that's very finite. And this will tie into our next subject, by the way, and you'll see as we kind of move forward. Now, this next little tidbit here where we start to talk about, the linear equation aspect of this, right? And if you guys were wondering, where's the linear in any of this? You guys might recognize this formula because if you're in an algebra class, this is one of those that they totally, politely beat you up on, right? It's like, oh yeah, I remember this. I hated this. Right. And that's the natural reaction of most math students. But this general equation where we have y equals mx plus b is really the way that we write a linear equation, and all of the variables and the letter names in here have specific meanings. Now, that equation can also be adjusted or resolved to make it equivalent to 0. And when you do that, the general form of the equation becomes I have two different x's, right? X1, x2 instead of x and y, right? I have a constant, right? And then I have my coefficients is what these are called, the multipliers. So the a would multiply against whatever that variable is. The b would multiply against whatever that variable is. And then this is a hard-coded number. And that all, when you add that all together, adds up to 0. Right. And that's a general form of the equation. When we keep it in this form, let's look at what it basically says. X and Y are coordinates of a point, right? So x1 and x2, x and y. M is the slope, and that means how far we go before we rise, right? So in other words, a slope M is equal to the rise over the run. This is all stuff you should have learned in math class, I hope, or are learning. And if you look at this graph here, we rise by 4 over a run of 5, which equals 0.8. So the slope is 0.8. The y on this side of the equation becomes the intercept. So B, right, is where we intercept the y-axis, which is at the number 4, right? So we have all the information on the screen here to completely populate this equation. The x is still going to be, the x and the y are still going to be unknown, but we know how that line's going to sit before we put any data. All the data that we would feed into this formula would fall exactly along that line because it has to. It has that slope, it has that y-intercept, and that's the line, right? So if you see a line going the other direction, or a really steep line, a really flat line, or a really vertical line, they all have a mathematical representation, but they sit as a line on a two-dimensional graph, right? And the slope, y-intercept, and all of those fancy terms I just used there. All right. What about an equation for 3D? All right. And it's like, well, you know what? We're just adding one dimension. This is where it gets kind of interesting. We just add, we have our X, Y, and Z, or if you will, our three X's, right? And those are the variable points. We still have a constant, which tells us where it intersects. But what we're doing when we create a three-dimensional space, when we have 3 points, we can dictate what we call a plane instead of a line. A plane is still linear, though. This is what's kind of interesting about this. It's flat, and it's basically a line in 3D space. So that's why we have linear two-dimensional things that are lines, or linear three-dimensional things, which are planes. And these are the equations for this. When it gets to doing hyperplanes, so more than 3 dimensions, okay, this is actually a graph of a hyperplane or a bunch of hyperplanes. Really hard to conceptualize, right? But in principle, you can have a plane that's got more than 1 dimension. This is very weird stuff, right? Don't try to wrap your head around it. Just go, next. All right. But there are equations for it. But I want to show you that as you add dimensions, you're just making the formula longer. You might not be able to create a graphic of it. Doesn't mean that you can't still work the math of it, right? That's the kind of the one of the takeaways. All right. So if you start looking at the equation of the hyperplane, and they're trying their best here to show you 3 dimensions, right? And then we're creating a hyperplane that's going to be relative to a plane, and they're showing you the points of it. And I'm not really trying to give you a really detailed explanation. I just want you to start thinking in your head, oh, wow, that's weird. That's pretty intense, right? Oh, you can prove all this stuff with math. Yeah. And here's the thing. The equations are considered simple because they're linear equations. What makes an equation linear? No exponents, no logarithms, no square roots, no imaginary numbers, right? When you start adding those other components in, then you start getting curved shapes. And if you think the planes are weird, the curved shapes are weirder, right? But a lot of what we do in numerical analysis, statistically, forms off of linear equations predominantly. Multiple variables, multiple coefficients, whether or not we can graph them, we can still do the math on them. All right. Then we get to this concept of dimensionality reduction, as they're calling it here. I always called it dimension reduction when I learned it. But here's an interesting graphic as you look at the screen, and I want you to think about this here. It says Reduction is the transformation of data from a high dimensional space to a low dimensional space. The low dimensional representation retains some of the meaningful properties of the original data. So let's just take a look at this graphic to see what they're talking about. So in the first graphic, we are working with a three-dimensional image, and they're trying to show you here that we have an X, a Y, and a Z, and then we have these cylinders, which are round at the top, round at the bottom, and have sides like a soda can, right? And that's representing a 3D object. Now, maybe as you look at this 3D object, you might say, well, the really important part of this 3D object is the two circles at the tops of those cylinders. So if I reduce from 3 dimensions to 2, I now have the two circles in an XY plane. Okay. Then if I want to reduce it, well, this is if I do XY. What if I do Y and Z instead? So in other words, instead of looking top down at those cans, so like instead of looking from here down, I'm now looking at it from the side. And what do I see? I see the same two tops, but I'm only seeing that slice of the top. So what you're seeing here is two different dimension reductions of the same 3D graphic on a different plane. On the one plane, they look like circles. On the other plane, they look like lines. Now, if we're trying to find, relevant information, we're trying to build a machine learning model, this little slice of data might be enough for us to train our model, and it's going to be less to train it on this data than it is on this three-dimensional data. And that's one of the key takeaways here is why do we do it? Right. So that's the next slide. Well crafted, PowerPoint crafter, whoever did that, right? The reason that we do that is, all right, this is a really good analogy if you read through it. So let's say you have a straight line, 100 yards, one-dimensional line, and you dropped a penny somewhere on that line. It wouldn't be too hard to find it because you just walk the line. How long does it take to walk 100 yards? Eventually, you'll find that penny because it's right on the line. You know that, right? I dropped it on the line. Just walk the line. There it is. All right, now let's add a second dimension. So instead of 100-yard line, now we're adding another dimension going across. So it's now long and wide, 100 yards square, and you drop the penny somewhere in that square. 100 yards by 100 yards, 300 feet by 300 feet. A lot harder to find it. It could literally, without a metal detector, probably take days. You'd have to find a system to like look every square inch or whatever, or whatever. It take a while. Now, if you also create a space that's 100 yards tall, like it says here, 30-story building the size of a football field, how long is that going to take you to find that penny? You see the reason for it. So if you can take a multi-dimensional object and reduce its dimensionality and just look at some aspects of it, you're reducing the amount of data that you need to process and therefore making it more efficient to build models, analyze models, look at data, etc. And this is a really key aspect of processing data because it takes a lot of computational power to do so when you're crunching the numbers and doing all of that. And so it says here, machine learning dimensionality simply refers to the number of features or columns in your data set, right? And we've already seen data set that have a lot, right? And it says here, more dimensions, more difficult to navigate through the space, more processing power to train AI models, which is training, very high computational needs. And it takes significantly more time to train a data set with more dimensions and features. Right, so that's one of the reasons. All right, let's look at some data sets now that have different numbers of dimensions. And they got an example here. It says, this data set contains information on all 802 Pokemon from all 7 generations of Pokemon, just in case you want to know. I'm not sure where they got this data set, but whatever. There's 41 features in columns in this data set. For example, the height, the weight, classification, egg steps, whatever that is, abilities, and I'm not a Pokemon person, so I just don't know. I do know that my daughter's got I think several 3-ring binders full of like Pokemon cards, right? Yeah, yeah. She's a full-grown adult, but she's still into Pokemon. That's the thing. All right. So if there's 41 features or columns, we can say it's a 41 dimension data set is the point, right? If we look at the iris data set, this really has 5 dimensions, right? 4 of them are numeric, 1 of them is just a label, right? And so we make that distinction too. Some are quantifiable numeric data points, some are qualitative data points, and some are just text or descriptions, right? And all of those are relevant, but they're still dimensions, right? There's a process for reducing these, and there's 2 generally large approaches, right? And so the one is called feature selection. So we're selecting specific features or a subset of the features to analyze, or we do feature extraction, which takes all the high dimensional data and converts it to a lower dimensional space. So for example, when we were doing like dot products, that kind of thing, combining it down to one number, that's a huge reduction. Taking like 2 rows of data and turning it into one number. That's huge, right? So, all right, one at a time. All right, so let's go to feature selection first. And I know this graphic is a little blurry and hard to read, but if you can make out, for example, what it says, when you do feature selection, it says, and I'm going through the graphic here, remove irrelevant features, right? Some stuff you really don't need to look at, increase the performance of our models, make training faster, it's easier to build, easier to understand, and easier to debug, right? Okay, makes sense. It says feature selection is the process of isolating the most consistent, non-redundant, and relevant features to use in the model construction. Sometimes this is a judgment call, but sometimes it's very clear as to what's really important or relevant. It methodically reduces the size of data sets, and as the size and the variety continues to grow. So, yeah, I mean, if you just keep bumping data into something and it keeps growing and you have more and more features in selection, you got to have ways to narrow it down to make it more efficient. Overall, it's trying to make the modeling more efficient. And one of the reasons for doing that is because there's a high cost for it. One of the reasons we're building all these data centers now, right? And why some communities are saying, hey, wait a second, we don't have enough power for these things, and that's been happening a lot lately if you follow the news. That's a thing. And you know what? Those machines cost money. It costs money to heat and cool them. It costs money to hook up the internet to them and have people run. You know what I mean? These are not light lifts, right? So more efficient we are modeling, the cheaper it is and better for all the equipment and everything. One thing I did notice on this slide, and I highlighted it with a red letter H, is they have this little table here and it's supposed to be height and weight, but they made it weight and weight. Somebody messed up. I'm just throwing that out there. Here's an example. All right, it says predict the weight of students based on the past information about similar students. So for example, this data set here has 4 features. Okay, one of them is not shown, but the one feature that was removed was the roll number. So maybe like an ID number. And then they have their age, their height, and their weight. Since like if you had like a student ID number in here, what impact would that have on height, weight, or anything like that? None, right? That's just an arbitrary number. So we can just eliminate that feature from the data set. We don't need to look at it, right? So right there, we're reducing by 1 dimension, right? So we went from 4 dimensions to 3 dimensions, much less computational power already, right? And because we're just dealing with the numeric data points here, it should be a lot more efficient and really ultimately give us like better answers when it comes down to it. So when we start to do this dimensionality reduction, there are 2 mathematical approaches to these. And it's been a while since I've touched this material, real frankly. So one of the things I did earlier today is I went to Chat GPT, and I don't know if I can recall this. I think this is, I guess, relatively interesting. So I'm trying to find the right browser tab here. Oh yeah, I did. Uh, yeah, I did this. So I went into Chat GPT and had them explain the formula. And I'm just showing it to you, right? And this is in the video, right? I thought about posting this into the course shell, but you guys can do the same prompt. So my prompt was principal component analysis, explain the formula. That was it, right? Um, and it tells you, it says it's a technique used to reduce the dimensionality of data while preserving as much variance as possible. And here's a breakdown of how it works. This is the core formula. Looks like a very simple formula, not scary looking, right? Um, and tells you what each of the variables is. Then it says first you center the data, and now the math starts looking a little scarier, right, as we go into these formulas. But I want to kind of break your mindset of this being afraid of the formula thing, right? This is just a representation, just like the first time you looked at computer code and go, what the heck is this, right? But now you can look at it and go, oh, I know what that is, right? Same thing here, right? These are just mathematical expressions that we could easily convert to Python code, right? We deal a lot with variable names and unknowns here because it's all in generic form, but you center the data, you find a covariance matrix. They talk about this in a little bit here. We find the eigenvalues and vectors, right? We sort and select, and then we project the data, and then they give you some stuff. And you know what? Even asked in the aftermath, let me know if you like a visual explanation of a code or a code example. So like if you wanted to, you could type in the same prompt that I did and get the same information. And then we got another formula to look at, which is the T-SNE. And this one does look a whole lot scarier. I'm just telling you that right now because it's doing a different thing. And this one's, we'll talk about this in the slides in just a moment. And this is a nonlinear dimensionality reduction technique for visualizing high dimensional data in 2 or 3 dimensions. So having way more than that, but trying to visualize it in 2 or 3. Right? This is the goal. It says the primary focus of this is preserving local neighborhoods, meaning the data that's close by the other data. They don't want to move it too far from each other, basically. The math looks very, very scary. Yeah, and there's lots of absolute values and etc. This is nonlinear, right? How do I know it's nonlinear? There's exponents, there's there's sum functions and all this stuff. This is a lot more. This is algebra speak that we're looking at right now. Not, excuse me, calculus speak that syntax basically we're looking at on the screen right now. It is nothing to be terrified of. This can be deciphered the same way a Python code string could be deciphered, right? Somebody took the time to figure out these formulas, and here they are, right? And yes, people have written Python libraries with these formulas already in them. So guess what? You don't have to create it from scratch. Thank you. Thank you, right? And this is the beautiful modern world we live in. But they show the procedure here of how to solve it, and I'm just scrolling through it. And this thing is really important in terms of working with this. There's also what we call a seed value that we throw in. And if your seed value is not right, it can break the whole thing. And that's a whole separate issue. All right, let's go back to the PowerPoint. Sorry about the little sideline. But those are kind of like what Chat GPT had to say about these formulas and what they look like mathematically. So once again, if you look at those formulas, you want to quit the class and not do this, right? So don't do that to yourself, right? You want to do this. It's just a formula, whatever, right? E equals MC squared is a formula too. Nothing too scary though. So let's dig into PCA a little bit. And here's what's kind of interesting about this is the notation that they're using here is a calculus style notation for doing proofs and stuff. So once again, take a breath, don't freak out to what I'm about to talk about here. But basically the way this works is it creates new variables by combining the original variables in such a way that the variance is maximized. So in other words, we're trying to take a variable and another variable and get it so that they vary as much as possible, that they vary a lot. And the way like this statement reads basically is maximize the variable t such that the various variables here, there's a wide enough distribution that it equals one. And if you learn about variance, variance goes from 0 to 1, and 1 is the maximum, basically 100%. So that is basically a way of writing what it says here. What value of W maximizes the variance of T subject to the constraint that the norm squared of W is equal to 1? Got that? Right? Yeah, completely irrelevant, but that's really what the formula says, right? Like if you were like a math guru, you would, define it that way. Now, the second part at the bottom there, it says T is a new variable that we have defined in terms of the original data. X is an optimal X. Okay, the original data is X, and the optimal vector weights of W, right? And so this is just a generalized form, and this question is highly pertinent, right? Okay, great. Thank you. What does that really mean? Okay, so here's what it means, right? All right. Right. See, the author of this PowerPoint's thinking a lot like me. It's like, I know you guys hate the math, but let's take it down a notch and look at it logically here. Here's a really great analogy of dimensional reduction. So this is feature reduction using a musical example. So let's say you play in a band and you have two keyboard players, there are three keyboard players, two bass players, a string section, a horn section, several percussionists, a bunch of singers, a couple of guitar players. All right, you got a big ensemble. And then great. And it says here, you're playing at Madison Square Garden. No problem. You all fit on the stage. But today you're playing at a little club in Racine. Uh-oh, we can't all fit on that stage. All right, we'll just take one keyboard player, one bass player, one percussionist, and he's going to play the bongos, one singer and one guitar player, and that's how we're doing the show. But what they've done is they've taken all the key elements of their band and boiled it down to these few instruments, which generally match the data on the left, but it's a reduced set of information, right? So I think this is a really good analogy for wrapping your head around it. They can still play the same song with the same arrangement and the same inflection. It's just not as many band members, right? Is it still the same song? It is, right? You haven't really changed the song. You've just changed how many instruments are playing it. So I think that's a really nice little analogy. All right. Now, if you apply this to a data set, okay, here's what they're kind of pointing out. All right. So here we have a data set that's plotted on top of an XY axis, and we look at it and go, oh, great. Scatter plot. Thank you. Right. We can see that the data, and you'll start to recognize this as a data person. When data kind of lines up, we call that highly correlated. Generally there's a pathway it follows, and it's linear. It's a line, right? And that can be reduced, right? So we're not even worried about the X and the Y here. We can just reduce it and combine it into these principal components, that there's this line and there's a certain amount of variance from that line. Sometimes it lands on the line or really close, and sometimes it's a little farther away. But generally speaking, it's a line, and it usually varies by about that much. And so I can take that complex set of data and switch it to a different format, and it's a lot more efficient, and it still really contains the same information embedded in it, and it's still useful for building our models. Now, I am going to go to this website, and when I clicked this link earlier today to test this PowerPoint, this took me to the website and the link wasn't working, and I'm not really sure why. And then I found it on the website, and updated the link here, and I don't know if like the link on the PowerPoint was broken or whatever, but I am going to go to this website and take a look at this stuff. What's really neat about this website, and you can play the videos if you wish, or you can go to the website and play with the actual graphs. They have a demonstration on this website of dimensionality reduction, moving from various formats, and you get to interact with it and change it. And you can grab the data points and move them. So I'm going to go up there and take a quick look at this. So I'm going to hit this really quick and bring that up. And here's, for example, this data set. All right, so here's one where they have a scatter plot, X and Y, right? And most of this stuff generally falls along this line. And in this case, this data is being transformed into this, it doesn't seem like it's less dimensions, but when you look at the graph down here, you see how the data is now conglomerated in one tiny little space, right? And if you take any one of these data points, and this is where it's kind of neat, like you can move the data points around, and the graphs interact. So have fun playing with it. And what's also very nice about this website is there's a nice little explanation, right? Kind of like, even if you don't get the math, you can see it being shown, basically. All right, so 2 dimensions to 1. And then here we have a 3D example, right? And you see, this is really helpful because the 3D is rotating. So you can see that it's got not only height and width, but depth, right? In 3-dimensional space, and the rotation helps a lot. And if I take all of that data and then convert it to a flattened 2-dimensional image, this is what happens. Now notice I can still, if I can grab one, it's not working. All right, I was able to do it before. I was able to grab some of the data points and move them. And then you can do it, take it even further. And this is what they're showing us. They're going from 3 dimensions to 2, and then from 2 dimensions to singular dimensions for each one of the axes. And it shows you basically that if I'm only looking at one aspect of the data, where the data sits. Okay, so think about this in terms of like data points. If one of the data points is relevant to what we're doing and the other one is not, I just eliminated the stuff that's not by doing this, right? And you can boil it down, and it's so much easier to deal with linear information like this than it is something more complex. So play with this stuff. This is kind of fun. I also found this was pretty amusing. They talk about, and I guess I sort of knew some of this stuff, but not all that much. I watched this video that's linked up here, and they talk about the United Kingdom and England and Great Britain, and I forget what other names they use for that country, right? And explain what all the differences were and how Northern Ireland was an outlier for all of them and whatever. Funny video to watch. I recommend that you check it out, by the way. All right, coming back. Cool website. Check it out. All right. Yeah. So why learn another method? PCA does have some limitations, right? When we start to work with correlations or formulas that are not linear, so we don't form straight lines or planes, PCA kind of falls apart a little bit. It doesn't really work well in that regard because your data is not on a plane, so I can't like invert it to make it sit nice and concisely. It's also can be kind of difficult, as it says, to interpret it. And when you have a significant number of dimensions, like more than like 5 or 10 or 20, it kind of falls apart a little bit in terms of efficiency. So those are situations where you wouldn't use it. So we use this other approach, the one that we kind of briefly looked at. And one of the goals of this approach, and what a mouthful, right? T-distributed stochastic neighborhood embedding. This is what this stands for. And I wouldn't bother to memorize that too much, but right. So it tries to optimize for preserving the topology of the data. So notice it says constructs a notion of which other points are its neighbors in trying to make all points that have the same number of neighbors. So in other words, kind of keeping them together. And I think I was mentioning that before. And because of the way the algorithm works, that it's really good at finding clusters of data or subclusters of data. And this technique is hugely popular in the deep learning area, where think about this, if you have really large data sets that have many features or columns, yeah, I could see why, right? The more data and the more depth of data, the more you might need this kind of approach. All right. There is this data set, and this is attached to our homework for Unit 3, which I have not published yet, but I will soon. There is this data set, and it's basically, this is a really weird data set. It's basically a data set, and I might have it open in Visual Studio Code. And in fact, if I do, I don't, but I can bring it up. So here's the data set. And if you look at it, what is it? It's a bunch of ones and zeros. Well, not exactly. It's a bunch of zeros and occasionally other numbers. You see the numbers here, right? And then notice at the very top, each column is a pixel. So in other words, this is a numeric data set that basically represents pixels from an image and their value, and each, so we're okay, so I'm going to backtrack just at the moment here. This is related to the whole concept of OCR, and this is one of the things that kind of blows my mind a little bit, because OCR technology, optical character recognition, has been around for a long time, right? It's not brand new. They were working on this back in the 70s and 80s. By the early 90s, regular consumers could buy OCR software, and with a scanner, you could feed in a document and turn the characters into text electronically. That's basically what we're looking at here. But in order to do this kind of a data analysis, think about this. If I was to do this with any certain font and type a number, a 7 in one font might look different than a 7 in a different font. Or if we did it with handwriting, the way I make my 7 might look different than your 7. I might put more of a slant on it, or I might do the European thing and put the slash in the middle, that kind of thing, right? And some people are left-handed, so they write on an angle, and some people are right-handed or whatever. And basically what they're doing here is they're taking this little grid that's 28 pixels by 28 pixels and then analyzing what the data points are inside of it, like where the character is and where the character isn't. And what they're doing here, basically, because it's a matrix, there's 28 by 28. If you multiply those together, that's 784 dimensions. Oh my God, talk about data points. And that's for one character. Mind-boggling, right? Mind blown, whatever, if you want to start like thinking about it that way. So this is a super high dimension data set. So there's 784 columns of data for each row. Whoa. Okay. This is why we need the 784 dimensions. So, oh my God. So if we want to start taking this data set and analyzing stuff, and this is kind of the point that we're making, or I was just making about characters, right? Like I could draw the number 1 and I could draw it like any one of these ways. And notice there's different tilts to it and all that kind of stuff. And then of course, if we like visualize that, I mean, I'll just like show you, and they're showing you where the numbers fall on the graph here after it's analyzed. But really what this is doing is it's clustering data, recognizing which numbers are which. And just like that very first chart that we looked at with the orange and the blue dots, and most of them fit over there and most of them fit over here. And once in a while, there's ones that aren't kind of where they're supposed to be. That's the person with bad handwriting, by the way. Right. And this little goofy graphic shows that they're taking the 784 dimensions, reducing it down to, I think, 3 here in this visual, and then clustering the points together. Right. This is pretty interesting. But there's this dimensionality reduction that's happening on a much higher level. We're going from 784 dimensions down to 3. That's huge, but we're still clustering the data, right? So this is why we use it in deep learning. So if I took that data and plotted it using PCA, I would come up with a graph like the one on the left. All right, now while all the different colors for each one of the numbers is present, man, they're overlapping each other. And you know what? I can't tell what's what, right? Here, where we're in a two-dimensional visualization using the other algorithm, the T-SNE, notice how the clusters are much more evident. You can still see there's overlap, right? Like, and this is like people with bad handwriting or whatever the case may be, but generally all the blues are here and all the reds are here and all the yellows are here, whatever, right? All the colors are basically together. So you can say with a pretty high degree of certainty what things are because of that. All right. So that's the relevant material for this unit. And there's a couple of discussion questions here, and I think that these are pretty good hard-hitting questions. Can we use this dimension reduction to somehow introduce bias in the data set? Maybe. Or would it reduce bias in the data set? Well, we could possibly do both. That's really kind of the point here. And why it's also to have diverse teams when you're working on this kind of stuff, when you're figuring out what you're reducing and why. Because let's face it, like you should really look at a person's data in order to hire them, not at their skin color or gender or whatever, nationality or accent or name. So I think these are really pretty important points. These are the key takeaways that you guys are supposed to take with you here. And we'll cap it there. Now, I am going to stop this recording here. So this is done.